Okay, so here's the question. You invest $1,000 on 100% annual interest. How much do you have after 1, 2, 3, and 10 years? And I got a very quick and good answer. After 1 year, you're going to have $2,000. Okay, because 100% interest means you take 100% of this and add it. Okay. After 2 years, well, you're going to take 100% of that, 2,000, and add it. You're going to get it with 4,000, and then 8,000, 16,000. After 10 years, you're going to have $1,024,000. Now, you're probably not going to find an investment that pays 100%. 5% these days is pretty good. Okay, so that's just choose that model because it's fun to play with those numbers. They're easy numbers to play with, and we understand what's going on. Now let's see how we write this out more formally. Okay. After 1 year, we have let's say $1,000 plus 1.00 times $1,000. 1.00 is 100%. Okay, because what does percent mean? It means per hundred. 100% means 100 per 100, which is 1. Okay, so we could write it out like that, and that equals times 1 plus 1.00. Now, 1 comes from this. In other words, I multiply $1,000 by this, I get $1,000 times 1, which is my original $1,000, and $1,000 times 1.00, which is $1,000 times my percentage. Okay. So that's $1,000 times 2. I'll write that as 2.00 because generally we're going to have percent here. Okay. Then after 2 years, it's going to be, and of course, this equals 2,000. We have ahead of myself, 2,000 plus 1.00 times 2,000 is 2,000 times 1 plus 1.00. And that's 4,000. I'm going to write this out more compact. There's 0. We have $1,000. Year 1. We have $1,000 times 1 plus 1.00, meaning we have $1,000 plus 100% of $1,000. Okay, and I'm not going to write that out anymore. After year 2, we have $1,000 times 1 plus 1.00. This is what we had before, right? And we multiply that by 1 plus 1.00. Okay? And of course, that equals $1,000 times 1 plus 1.00 squared. Okay? For the third year, then we have $1,000 times 1 plus 1.00 squared times 1 plus 1.00, which is $1,000 times 1 plus 1.00 cubed. Okay? That makes sense? So if we go down to 10 years, every year we're going to multiply by another 1 plus 1.00, which is going to increase this power by 1 each year. I mean, all this is saying is in 3 years, we multiply by 1.001, 2, 3 times. In 10 years, we'll have done it 10 times. And I hope I'm recording this. Yeah. Okay. We'll have done it 10 times, and we get okay, get this. After T years, we get $1,000 times 1 plus 1.00 to the T. Okay. And of course, 1 plus 1.00 is just 2. %100 annual interest. Gives us, we'll call it P for principal of T equals $1,000 times 2.00 to the T. Okay. Well, 2 to the T is just our toolkit exponential. Because it's a graph where this line down here is y equals 1,000. And we can see how the money's growing. Okay. Now, we're going to compound this $1,000. So pound quarterly. That means that the annual 100% interest. It means add 100% over 4, which is 45%. Four times per year. Okay. It's the same as multiplying by 1 plus 0.25 4 times per year. Now I could break that down, multiply 1,000 by 1.25, you're going to get $1,250. Okay? Because 25% of 1,000 is 250. Add that to 1,000, you get 1,250. Okay? It's the same as multiplying by 1 plus 0.25. Okay? And then you take that 1,250 and add 25%. And that's going to give you more money. And you take that money and add 25% and do that again, you're going to have significantly more than just $2,000 after a year. I'll break it down. Zero, 1/4, 1/2, 3/4, 1. At year 0, you have $1,000. At year 1/4, that's the first quarter, you have 1,000 times 1 plus 2.25. 1,000 times 1 is your $1,000 that you get to keep. And times 0.25 is your interest. That's $250 interest. You end up with 12. And then you get 1,000 times 1 plus 0.25. That's what you have here. Then you get to multiply that. 1 plus 0.25. And that equals 1,000 times 1 plus 0.25 squared. And then we multiply again. I'm not going to write it out for 3/4, but at the end of a year, you have 1,000 times 1 plus 0.25 to the 4th power. Okay. Now I can sort of calculate that. 1 plus 0.25, of course, is 1.25 to the 4th. And that's 5/4 to the 4th, which is 625 over 256, which is pretty close to 2.5. Okay. That's approximately $2,500. And you put that into your calculator and calculate exactly what it'll be. Okay. Well, then, your your effective interest is $1,500, which is 150% of $1,000. Okay. So 100% interest compounded quarterly is really like getting 150% interest. You're getting $500 more than you would if you just did simple interest. Okay. We go on with this. To remedy that. Okay. Next, let's think about we're going to compound it 10 times. Now remember, not compounding it, we made $1,000 in a year. Compounding it 4 times, that was up to 2,500. What's going to happen if we compound it 10 times? Now you're going to need to use your calculator for this. I can't calculate. Yeah, I can estimate what it would be because you know what the limiting value is. So you get you end up with this at the end of a year. Why? Because this is 1/10 of your 100%. Okay. And we do it 10 times. Okay. Compare with what we did just a minute ago. So we compare what we did a minute ago was adding 1/4 of 100%. Times. Okay. Now, instead of 1.00 over 10, I'll just abbreviate it 1 over 10. And actually, I don't want to do that. I want to keep that 1.00 to remind you that that's your 100%. Okay. And the 10th equals your calculator. You can just do 1.1 to the 10th, right? So do that, and I think you're going to end up with something like 2670. Not just a ballpark estimate. It'd be too far off. What do you get? I got a little carried away. What you got was 25, something pretty close to 2,600. Okay. Okay, well, let's compound it. Let's compound it 52 times. Now let's notice that when we did $1,000 simple interest, we gained $1,000. When we did orderly compounding, we gained $1,500. Okay. When we went to compounding 10 times, we went up to $2,600, right? Now, the big jump was from 2,000 to 2,500. By going from 4 times to 10 times, we only went up another 100. Okay. Well, if we do it 52 times, that's going to be 1,000 times 1 plus 1.00 over 52 raised to the 52nd power. So could you punch that into your calculator, see what you got? Okay, I get 2670, but it's actually 2690. Okay. Well, did we get much of a jump going from 10 times to 52 times? Not much of a jump. To $90, especially if you're investing long term, that grows and things will be different later. Okay. Okay, well, let's just do compound 1,000 times. That means you're going to have $1,000 times 1 plus your 100% interest divided by 1,000 to the 1,000th power, which is $1,000 times 1.001 to the 1,000th. What do you get? No, I'm pretty sure we're pretty close to $2,718. Okay, well, I was off a little bit on this. It's 2770. Okay. Now, we compound 1,000,000 times or 1,000,000,000 or any number of times we want to, we'll never get to 2719. Okay. Okay, now you notice what we've done in each of these cases. If we let n be the number of times we compound, what do we got? 1 plus 1 over n raised to the n. Here we've got 1 plus 1 over n raised to the n, where n is now 52, right? Here we let n equal 1,000. We get 1 plus 1 over 1,000 to the 1,000, 1 plus 1 over n to the n. Limiting value of 1 plus 1 over n if n approaches infinity is e. That e to the x thing, which is approximately. Thanks again, Sandy.
Get rid of boxes, so I worked on in that.
Thank you. The most you could get from compounding as many times as you want is $2,718.28. Okay, and I would get the 29 cents unless somebody is really generous and rounds up that last penny. Okay? So continuous compounding at annual rate R. We'll stick with $1,000 for a minute. I'm going to write down the experiment I've written down so many times, which is what we use for continuous compounding. For continuous compounding, it's 1,000 times e to the r. And this is where e comes from. Okay? If you understand this, you have some feeling of what E is, and it makes it easier to work many of the problems that you have to do. Okay? So that's the key. Now there's a connection from here to here. Why is it 1,000 times e to the RT? Well, that involves a little bit of algebra that I'll probably talk about a little bit later. If we accept that the limit is of 1 plus 1 over n to the n is this, is e. Then if we replace this n by an r, we do a change of variable and replace this n by something else, and we get e to the RT. In general, continuous compounding P of t, not 1,000 e to the RT, it's P naught e to the RT, where P naught's what you start with. Okay? For compounding n times, It's this formula that your book gives you without a complete explanation. And I think people are starting to think that you're actually teaching pre-calculus if you teach people to use this formula. You're not teaching pre-calculus. All you do is teach people to use this formula. You're teaching finance. And if you're going to teach finance, since finance ends up being intensely mathematical, so far beyond what we're doing here that you wouldn't believe it. I don't even know it. Okay. Although I do have the analytical skills and stuff to do a good bit of it. I focus on physics, not finance. Of course, half the people working in finance at the high level are PhD physicists.
Mhm.
But they know a lot more than I do, and they're smarter than I am too, a lot smarter. Okay. Anyhow, that's kind of the story of compound interest, and that's where E comes from. And it doesn't apply just to money. Continuous growth of pretty much anything at a constant annual rate R is P of T equals P naught e to the RT. Okay, let's say that the total of all your investments in the year 2030 is $600,000. Okay, so 2030, $600,000. And then in 2035, let's say it's $750,000. And how do you figure out your effective annual rate of compounding? Okay, that's the question. I'm going to put it up here on the board. And what you want to do is these next items works drier than this. Put that information on. Can you put that information on? Go ahead. So let's say that in 2030, somebody's investments, your investments, hopefully there's more than that, but that's okay. Okay. So $600,000, total $600,000. And in 2035, they totaled $750,000. What can we figure out? Well, Still continued growth at a constant rate. Well, then, it makes sense. Information on the graph. Now, today, it's it's 2025. Okay, it's 2025, right? And we're talking about 2035 and 2030 and 2035. So let's just say T equals 10, which of course is the year 2035. If 2025 is T equals 0, and we have T equals 5, which is 2030. And we've got $600,000. Okay, so let's call this axis P, the principal, we'll call this axis T. Okay, so instead of saying Y equals 600,000, which you could, you call that Y if you want, but I'm going to call it P. I'm going to say P equals 600,000. Then I have this point on the graph. In here, I have the point P equals 750,000. Now I can estimate an exponential curve here. Okay, and it's probably going to look something like this. Not particularly accurate, but it's going to look something like this. Okay, and this is going to be equal P naught times B to the T. It's not an E to the RT because you don't know how to deal with E to the RT yet. You will by next week. Okay, so we can redo this with an E to the RT. But how are you going to determine? Well, there are two things that are unknown in this model. The value of P naught and the value of B. So what do? You've got 2 points on the graph. Just like we did, you have 2 points on the graph of a linear function. You can plug in the information from the 2 points. And each point is going to give you an equation. The first point P of T equals 600,000, T equals 5. We plug that information into our model. P of T equals P naught B to the T. And we get P of T is 600,000. equals P naught times B to the fifth. In the second point, we get 750,000 equals P naught times B to the 10th. Not written very well, but I'm going to rewrite it up here. Okay, we see that? Here's our model. We take the P of T for T equals 5 and plug it in here. And let T equal 5. We get this equation. And similarly to the second equation. So our equations. I want to solve these two equations. For P naught and B. So how do we do that? And we can divide both sides by B to the fifth, and then we'll have P naught, right? Now that still doesn't give us the number for P naught, but it gives us an expression that we can then take back to our second equation. We take this expression and plug it in here into our second equation. And that gives us the equation 600,000 over B to the fifth I left part of the equation out. Let me do it right. Also, I wanted to switch colors here. Okay, this 600,000 over B to the fifth, I'll just write in blue. That's this, times B to the 10th. That's going to equal 750,000. Okay. Well, what's B to the 10th divided by B to the fifth? It's B to the fifth. Okay. So subtract this exponent from that one because we're dividing. And of course, got to be pretty good with the rules of exponents. Okay. Can you solve that for B? First thing you do, well, you got to divide both sides by 600,000. Now we get rid of all the zeros. We get B to the fifth equals 1.5. Okay. Because 150 is 1/4 of 600, so I'm pretty sure my decimal's right there. If not, you can always go back and correct my numbers. So how do we solve this for B? I'm just rewriting it up here so we see where this goes. B to the fifth to the 1/5, B 1.25 to the 1/5, right? So what's B to the fifth to the 1/5? Well, if you do a power of a power, you multiply the powers. So that's B to the 5 times 1/5 equals 1.25 to the 1/5. That's just B to the 1. Because 5 times 1/5 is 1. Now, what's the 1/5 power of 1.25? Can you plug that into your calculator? It's probably going to be around 1.04. 1.04 something. Okay, so 5 times 1/5 is 1, so this is B to the 1. Punch that into your calculator, you get 1.046. So that's rounded off some. Okay. Well, that's 1 plus 0.046. With this model, this means that every year you keep your principal and add 4.6%. Okay. You can interpret this as this means we're adding 4.6 every year. And your effective interest rate is 0.6%. If your investments are growing at 4.6%, right now, that's not too bad. Okay. Most people would take that at this point. Okay. Especially given all the economic turmoil due to this tariff situation. Okay. And that situation is brand new. Nobody knows where it's going. Could be really good, could be really bad, depending who you ask. Okay, well, this isn't confined to money. I could phrase the same thing as okay, let's say it's 10 years down the road. 10 years goes a lot faster than you think it will. That, um, but we measured the number of fish in the lake. Okay? That's exactly the same problem this is. This is money, these are fish. But they're same. Model would apply. Okay. Now, one thing we haven't calculated is P naught. Okay, we haven't completed this problem either, but we've interpreted what the effective rate is. Now, we might as well find out what P naught is. P naught would be population at T equals 0. Okay, how do we get P naught? Well, remember that back here, we said that P naught was 600,000 over B to the fifth. Now that we know B, it's about 1.046. Then we just replace B with 1.046. What do you get? If you do 600,000 divided by 1.046 to the fifth. Okay, so you got 479,173. That's because you used the rounded off 0.046. If you'd used all the numbers that your calculator gave you here, instead of rounding off, you would have ended up with very, very close to 480,000. Okay. Since this is rounded up a little bit, this number is going to be a little too big. So you're going to get a little less than 480,000. Now, how did I know that that was going to be 480,000? Well, it's pretty easy. I have the same interval here as I have here. I have a 5-year interval here and a 5-year interval here. Now, 600,000 is 4/5 or 80% of 750,000. So in this 5 years, if I start here this number is gonna be 80% of this number. So this number should be 80% of this number, and it's no trick to figure out 80% of 600,000. Now, the other big deal that we're gonna talk about quite a bit in class, and I'll go back over this model in class, because people need to understand it and really ought to tune into this video. Since I don't think a lot of this has been explained by open math. The other thing is, for an exponential function, we're gonna have a constant doubling time. Okay? And you know that because you know how to construct what does it do? Every time you go over one, you go up one. Each of these lines is twice as close to the bottom, the lower edge of the rectangle as the one above it, right? So every time you go from one of these lines to another, you're doubling. In other words, this line here, the one that this axis is twice as far from the axis as this one. And this one is twice as far as this one, and this one is twice as far as this one, this is twice as far as this one. So you have in our toolkit y equals 2 to the t or 2 to the x function. Have a constant doubling time. From here to here it doubles, from here to here it doubles, from here to here it doubles, from here to here it doubles. And we'll talk about that and move on toward the idea of using logarithms to figure out doubling times.